Hello, I made a video to talk about working with series that have negative terms. All of this stuff is something that we looked at in class, but I wanted to go through a few examples to show you how the different steps fit together. So if you think back to the tests for convergence of series, most of them only applied to positive term series. That's like the integral test, the comparison test, and so on. But a lot of times we will work with problems where we have both positive and negative terms, especially if we define a function of x as a series, because then it's possible that x could be negative. So when we encounter one of these series that has negative numbers, there's three things that we can use. So it's the divergence test, absolute convergence, and the alternating series test. I want to take a look at how we apply these three steps on a couple examples. And when we do this, it's going to be easiest if we go through the steps in order. And you'll see why that is in just a minute. Here's the first example that I want to look at. Okay, so we're going to analyze the following series and see if it converges. We want to go through the steps in order, and so the first step that I do is apply the divergence test. To apply this test, I'm going to take the limit of the individual terms in the series, and if this limit is not 0, the test tells us that the series diverges. For the example that we're working on, the setup for the divergence test looks like this. Now we have a power of -1 in front of the square root. I'm going to deal with that by breaking the problem up into two separate cases. So -1 to the j plus 1 power is 1 if j is odd, and it's equal to -1 if j is even. If you're having trouble seeing where this pattern comes from, put in the first few values of j, 1, 2, 3, and see what happens to these powers. To finish off this step, I'm going to evaluate these two limits separately. So I broke up the limit for the divergence test like so. We have one limit when j is odd and one when j is even. I'm going to work on them both at the same time. In the next step, I factor out the highest power in the numerator and denominator of the fraction. And then when I take the limit, it simplifies to the following. And so I get 1n minus 1. This means the limit does not exist. In the limit, our sequence is bouncing back and forth between two different numbers. In a case like this, the divergence test tells us that the series diverges. The limit that we took is not equal to 0. So now we're done with this problem. We know the convergence behavior of the series we're analyzing. We don't need to go on and look at steps 2 and 3. That was our first example. Let's take a look at another example. So we're going to analyze the following series. Again, we see that we have some positive and some negative terms. First step, I'm going to apply the divergence test, just as we did in our last example. Here's the setup for the limit that we want to take. And now I'm going to do the same shortcut that I did last time. I'm breaking the problem up into the case where j is odd and the case where j is even. I'm going to write that idea in a little bit more compact form. I'm just putting a plus or minus in front of the limit. All right, then when we take the limit that we have left, we get plus or minus 0, and this, of course, is just equal to 0. When we apply the divergence test and we get a value of 0, that means that the test is inconclusive. So for this example, we're going to go on to our next step, and here we're going to determine if the series converges absolutely. So we start with our original problem, and we take a look at the related problem that we get by taking the absolute value of every term. One thing we talked about in class last week, if this series of absolute values converges, then we know that our original series that had positive and negative terms also converges. Why would we want to do this? Well, remember that we had 4 or 5 different ways to analyze series with positive terms. And so once we take the absolute value, we can use those tests because the absolute value makes all of our terms positive. Okay, so let's apply that to the example that we're looking at. I took the absolute value of my terms here, and now I'm going to simplify. For the problem we're looking at, it simplifies down to the sum of 1 over j cubed. Remember, we know from the notation on our summation symbol that j is between 1 and infinity, and so j cubed is always positive. On the top, we have a power of minus 1. When we take the absolute value of that, we always get just 1. Okay, does this help us? Yes, it does. The series that we got by taking absolute values is something that we've seen before. We call it a p-series. And since p equals 3, we know that this series converges. So now we apply the theorem on absolute convergence. Our original series made up of positive and negative terms also converges. We're done with this problem. We don't need to go on to step 3. We've determined what happens as far as the convergence behavior goes in this example. And remember, in a case where the series of absolute values converges, we say that the original series converges absolutely. That was our second example. I have one final problem that I want to take a look at. So we're going to analyze this series. Again, we start with step 1. We apply the divergence test. Here's the limit that we need to evaluate. Again, I simplified the cases of odd j and even j by putting a plus or minus sign in front of the limit. When we have roots, the idea of factoring out the highest power of j looks like this. And then I can simplify. In the limit, I know that fraction 8 over j is going to go to 0. I evaluate the following limit, and that is also 0. Just like our last problem, the result of the divergence test here is inconclusive. I'm going to go on to the next step in my problem. So we're going to take the absolute value of each term and see if the resulting series converges. Here's the setup. I took the absolute value of the terms in my original problem, and it simplifies like that. Okay, on top, we know the absolute value of 1 or negative 1 is always 1. And also, if you look at the cube root in the denominator, that's also going to be positive. So we can get rid of the absolute value signs and simplify it as shown. When we have a series involving roots, that usually suggests the limit comparison test. Here I'm going to compare with the series 1 over j to the 1/3. Why did I pick that? Well, remember on step 1, when we factored out the highest power in the denominator, that power was j to the 1/3. So that gives me my comparison series. This is also a p-series. P is equal to 1/3. This means that our series diverges since p is less than or equal to 1. Remember that we're trying to set up the limit comparison test. When we do this with a divergent series, it goes on top of the fraction. That gives me the following setup. I plugged in the values of the two series, the familiar one on top, the example that we're looking at on the bottom. Now I apply my algebra of fractions and simplify the result. On the next step, we're going to use a property of exponentials. So when we have multiplication or division of two things that have the same exponent, we can simplify them as shown. Now I'm ready to finish this off. The fraction inside the power, okay, we factor it as follows, and we see that the resulting limit is 1. Now we've got to compare this result to the limit comparison test. Our limit is a finite positive number. The series that we were comparing diverges. And so we conclude that the other series diverges as well. Now this means that our absolute convergence, that test is inconclusive. What do I mean by that? Okay, well, on our last step, we showed that this series of positive terms, 1 over the cube root of j plus 8, we showed that that series diverges. But remember, that was just one step in analyzing a series with positive and negative terms. Just because the absolute value series diverges does not mean that our original series diverges. That's not what the test of absolute convergence tells us. It only tells us something if we get a convergent series when we take the absolute values. All right, so the result of step 2 on this example was inconclusive. That means we're going to go on to our final step for dealing with series of negative terms. That's called the alternating series test. This test is a bit restricted. We have to have series that alternate between plus and minus. The example that we're working on here does do that, so we can use this test. And as a reminder, here's what the alternating series test says. It has 2 parts. We're going to look at both parts separately, but notice that the limit in part B is something that we've already seen. That's the same limit that we use when we calculate the divergence test. So we've actually completed that part of the problem. We did that on an earlier step. All right, now I want to look at part A. It's an inequality involving the absolute value of the terms of the series, and it says that they have to be decreasing. So I want to look at 2 ways we could approach this problem. First, I'm just going to calculate some of the values using the formula that we started with. Okay, so I plugged in my original formula. I put in 1, 2, 3, and 4 for j. Then I simplified the absolute value and I got these expressions. What I did next was put those into my calculator to see what decimals I was getting. I got the following sequence, and we see that, yes, these numbers are decreasing. So based on the pattern that I see here, I'm going to conclude that the absolute value of the terms is decreasing. Now this is okay. This is a good way to start our analysis of this kind of problem. And if you were to do this on the exam, that would be good. But it's not completely precise. We really want to consider what happens to all the terms of the series. And so the best way, the most rigorous way to set up this problem is to look at the absolute value in part A and do some algebra on that inequality. Here's the statement from the alternating series test. So I want to prove that this is true. I plugged in the formula for the specific series that we're working on in this example, and then I simplified the absolute values. On the next step, I'm going to take the reciprocal of both sides of that fraction, and remember that when you do that, you're going to reverse the direction of the inequality. That's true because both of the numbers that I'm working with are positive. All right, I'm going to cube both sides. Now, when I cube both sides, the inequality stays the same direction as long as the numbers that I'm cubing are both 1 or greater. If you look at what happens in this problem, you'll see that that is true based on the values of j that we have in our series. And then my final step looks like that. So what we conclude from this work, the last step that we got, 9 greater than 8, that's definitely true. And this means that our original inequality comparing the terms of the series, that is true as well. So as I said, this is the best way to show that that property is true. There's a lot of subtle points working with these inequalities. And so if you want, you can use kind of the shortcut method where we just use our calculator to find some terms. All right, what we conclude from this work, the series that we're analyzing satisfies requirement A for the alternating series test. The other requirement we have to meet is this, the following limit. As we said before, this is the same limit that we looked at in the divergence test. We evaluated this limit on step 1 of the current example, and we showed that yes, it does in fact equal 0. So we have shown that our series satisfies both of the requirements for the alternating series test, and so this particular example converges. If we have a series like this with positive and negative terms, where the series converges, but the series of absolute values does not converge, the term for that, we say that that series converges conditionally. And to determine that, I had to do steps 2 and 3 for my last example. All right, that's it. That's a review of the steps that we use when we're working with series that have both positive and negative terms.